This is slide number 43 and I am your presenter Asloob Mudassar. Transfer function of Fresnel diffraction formula. You know that there is a relationship between the transfer function and the point spread function. The Fourier transform of the point spread function is regarded as transfer function. So the Fourier point spread function we have calculated for the Fresnel case was represented by kappa at x comma y. So let's take the Fourier transform of the kappa on both sides. So the Fourier transform of kappa on the left hand side is equal to the Fourier transform of its expression, that is the expression of kappa on the right hand side, which is equal to e to the power iota kz over iota lambda z multiplied by the exponential e to the power iota k over 2z. Within the bracket we have x square plus y square, and this is equation number 18. Now you see that we have to calculate on the left hand side the Fourier transform of kappa can be represented as capital K at the Fourier variables fx comma fy. And on the right hand side we can write this quantity, that is e to the power iota kz over iota lambda z as such, and we can take the Fourier transform of the quantities within the curly bracket. And in writing the quantities in the curly bracket, we have written k is equal to 2 pi over lambda in the previous expression and obtained this relationship. Now you see that in this relationship I am going to introduce n square factor over here. What is n square? Look at the end, that n square is equal to 1 over iota lambda z. So I have introduced n square over here. And also n square was introduced into the exponent, that is e to the power minus pi n square within the bracket x square plus y square. So the purpose of writing n square is that we can write down the Fourier transform of this quantity directly using n square before the Fourier operator and also n square present in the exponent. So in this shape we can directly write the Fourier transform as given in the next step. So we have e to the power iota kz, the term that was already present, and now the Fourier transform is e to the power minus e to the power minus pi over n square, and within the bracket we have fx square plus fy square. And then we can write it in the form, that is we can substitute the value of n square back over here because we have written the Fourier transform for which we used n square factor, and then we are replacing n square by its original value, and we get e to the power iota kz multiplied by e to the power minus iota pi lambda z within the bracket fx square plus fy square. So this is actually equation number 19. In obtaining equation number 19, the Fourier integral was separated into two integrals in the x and y variables and solved one of the integrals. The other integral was similar, and the combined result is shown in figure 19. So you see that in figure, actually not in the 19 but in the following figure, maybe for example in equation number 20. So we defined the constant here. In order to solve this equation we are going to define some constant. In equation number 19 you see that there is an integral, that is the Fourier integral, that the expression for the evaluation of the Fourier integral is what we have omitted, and we have directly written the expression, the end expression of the Fourier transform in equation number 19. Now we are going to explain some steps that helped us in order to evaluate the Fourier transform, and for that one we introduced alpha is equal to minus n square pi, employed the computing the square method to the expression over here. So here we are applying that is, for example, here in this curly bracket we are going to apply the completing the square method, which is e to the power within the square bracket we have alpha x square minus iota 2 pi fxx, and this is now converted into by completing the square on the right hand side, that e to the power alpha, and within the parenthesis we have x minus iota pi fx over alpha whole square, and then another term e to the power alpha within the bracket pi fx over alpha whole square. So you see that you can see the term in the exponent which has a complete square, which has been written in the form of a complete square. So using the integral, that is integration from minus infinity to plus infinity e to the power minus alpha t square dt is equal to pi over alpha, the square root of pi over alpha. where t is equal to x minus iota pi fx over alpha. So you see that we know that this is a well-known integral, and we know the value of t over here also, and then we are substituting the value of these parameters, that is you can substitute the value of t, there is no need to substitute the value of t and to substitute the value, just put the value of alpha over here in this equation, because the solution of that integral is pi over alpha, square root of this quantity. So you put the value of alpha, which is equal to minus n square pi over here, and then we can finally obtain the result, that is the transfer function in the Fresnel domain is equal to e to the power iota k z multiplied by e to the power minus iota pi lambda z, and within the bracket we have fx square plus fy square. This is equation number 20. For comparison, the free space propagation transfer function derived earlier is reproduced below. Actually, in order to make the comparison of the Fresnel transfer function with the free space transfer function, we are going to write down the free space transfer function as given in equation number 21. You can see that this is the term, and this term which is in the curly bracket on the right hand side e to the power iota 2 pi over lambda, and the square root of 1 minus lambda fx square minus lambda fy square multiplied by z, which is outside the square root sign. And you know that the limit is that fx square plus fy square, the square root of this quantity is less than equal to 1 over lambda, and otherwise this quantity is equal to 0. So you know that we are assuming we actually want to write down the free space propagation factor, or the free space transfer function to the we wanted to convert it into the Fresnel transfer function. For that one, we are assuming that the mod of lambda fx square is less than 1, and similarly the mod of lambda fy is less than 1. We can expand the radical term, that is the term within the square root, that is 1 minus lambda fx square minus lambda fy square, the square root of this one. So finally we obtain equation number 22. And in the equation number 22, we have 1 minus lambda fx square minus lambda fy square, square root of this quantity on the left hand side is approximately equal to the first two terms we have indicated on the right hand side in equation number 20, that is 1 minus half, within the curly bracket we have lambda fx whole square plus lambda fy whole square, and plus so on. The other terms are not shown. So equation 21 becomes under this condition, that is the capital K at fx fy z, that is the free space propagation factor is approximately equal to e to the power iota k z multiplied by e to the power minus iota pi lambda z. Within the bracket we have fx square plus fy square, and implies that that this holds when fx square plus fy square, the square root of this quantity is 3 times less than the symbol we have used, is much less than 1 over lambda. Otherwise this quantity is equal to 0. So you know that now in the free space propagation free space transfer function k, you can see that the non-zero quantities, which is e to the power iota kz multiplied by e to the power minus iota pi lambda z, within the bracket we have fx square plus fy square is actually the same quantity as appear in the Fresnel transfer function, that is this one. So restriction to smaller values of fx and fy means allowing the smaller values of angles involved in the angular spectrum propagation. So comparison of equation 20 and 23 gives that is the transfer function of the free space propagation is the same as the transfer function obtained from the Fresnel calculations as shown in equation number 24. But the condition is that we have to work under the small angle approximation. So these small angle approximations were applied to the transfer function of the free space, which converted into the transfer function of the Fresnel. So we can say that the transfer function in the free space, which is capital K of fx, fy, z, is actually providing the superset. You know that in this case, or you can say that the super transfer function, which can be converted into the Fresnel transfer function. So we can say that is the free space propagation transfer function reduces to Fresnel field transfer function under small angle approximations. Propagation of transfer function involves propagation of plane waves at different angles, and limiting these angles to smaller values means that only the plane waves at smaller angles contribute to the Fresnel transfer function and thus the Fresnel field. So you see that here we obtained the condition that when we write the transfer function of the Fresnel, it means that the built-in quality, the built-in characteristic of this which we obtained from the transfer function of the free space is that small angles are involved. That is, the Fresnel transfer function holds under the small angle approximations applied on fx and fy. So we can equate the two transfer functions. Now we have a Fresnel diffraction formula for confocal spherical surfaces. You see that we have already derived the Fresnel diffraction formula and see the conditions under which those were obtained. Now we are deriving the Fresnel diffraction formula for confocal spherical surfaces. What are the confocal surfaces? You can see that these are the confocal surfaces. We have two planes, zeta and eta plane, and another parallel plane parallel to the zeta eta plane is the xy plane located at a distance capital Z from that one. So at Z is equal to 0 we have the zeta eta plane, and you know that we have a point P on that plane, but point P1 is located on the spherical cap shown over here, and the plane is tangent to the spherical cap. On the right hand side we have another spherical cap, and P0 is any point, the P0 is any point of observation on this spherical cap, and you know that this spherical cap is also tangent to the xy plane. So let's read the statements. Two spherical surfaces are said to be confocal if the center of curvature of one surface lies on the other and vice versa. The first spherical cap is tangent to the zeta eta plane. The second spherical cap is tangent to the xy plane. Both planes are parallel to each other and are separated by a distance capital Z. This is shown in the figure. The field at the input zeta eta plane is known and is represented by u of zeta comma eta. So this field is known at the left spherical cap, and the problem is to find the field at an arbitrary point P0 lying on the second spherical cap at a distance r01 from the point P1 lying on the first spherical cap. So we have to find the field at the point P0 due to the field u which is at point zeta and eta available at the point P1. Fresnel formulas equation number 9, 11 and 14 are not appropriate for this problem. So let's start with the equation number 4 given next, which is the backbone of equation number 9, 11 and 14. So you see that the equations, the Fresnel formulas in equation number 9, 11 and 14 were derived from equation number 4, which is given in equation number, which is reproduced in equation number 25. So we have q of xy, that's the field at the point xy is equal to z over iota lambda, and the summation is over the whole clear aperture S1, and we have the field at a point within S1 represented by u of zeta comma eta, and we have some terms over there e to the power iota k r01 over r01 square, and the integration is with respect to d zeta and d eta. So u of x comma y is the output field at point P naught, which we have to find. The radius of curvature of each spherical cap is equal to capital Z. So the radius of curvature of each spherical cap is equal to capital Z. Next we want to find the distance r01 between P0 and P1 under Fresnel approximation, treating the spherical caps with parabolic surfaces. So we define the two coordinate system on the z axis for the left spherical cap and for the right spherical cap. So capital O at x0, y0, z is equal to capital Z is the point where the right spherical cap pierces the z axis. And you know that we have written down this coordinate with respect to the origin, which is point B on the left, which is the point B, and the coordinate of a point B is zeta is equal to 0, eta is equal to 0, z is equal to 0 is the point on the left spherical cap piercing the z axis, the origin of the coordinate system. So D is any arbitrary point on the left spherical cap at the that stands for point P1. So you see that in this figure you can see that we have replaced the point P1 P1 by a more general point D. So D stands for the point P1 that is on the spherical cap given that is the left hand spherical cap. So we have to find out the coordinate of a point D, capital D. For that one, D is an arbitrary point on the left spherical cap that stands for P1. We have to find the coordinates of a point D using the geometry shown where delta of zeta comma eta is given by. So this delta of zeta comma eta is equal to r minus square root of r square minus zeta square minus eta square is equal to capital R, and within the parenthesis we have 1 minus square root of 1 minus zeta square plus eta square over r square. This is equation number 26, which we are going to explain that where delta of zeta and eta exist and how we computed that one. So look at the figure over here. So OD is actually equal to capital R or equal to capital Z, and similarly O to capital B is also equal to capital R capital Z because this stands for the radius of this curvature. So OD and OB are the same in distance and they are equal to capital R is equal to capital Z. Okay, now you see that we have a point D, and just before the point D, so AD is actually perpendicular to OB. AD is perpendicular to OB, and you know that we have a triangle. In order to reach point D, we have to go from A to C and then from C to D. So A to C is represented by a general coordinate zeta, and C to D is represented by the general coordinate eta. So at C you have a right angle triangle. So if you consider the right angle triangle AC and D, you can write the value of AD as zeta square plus eta square, the square root of the whole quantity. So using the Pythagoras theorem, we have written down the value of AD. Okay, now we know that O to capital B is actually capital R, and O to A can be calculated using the Pythagoras theorem applied to the triangle OA and D, and at A we have the right angle triangle, so we can apply the Pythagoras theorem to find out the side which is OA, and OA is given by r square minus zeta square minus eta square, the square root of this whole quantity. Because one side is r is equal to z, the other side is zeta square plus eta square, the square root of this quantity, and the third side which is OA can be computed using the Pythagoras theorem, which is equal to the square root of r square minus zeta square minus eta square. So we have calculated OA, and we know the value of O into capital B, which is equal to capital R. So we can find out from B to A. B to A is equal to OB minus BA, and BA is nothing but delta of zeta and eta. So we have written over here that delta of zeta and eta is equal to capital R, which is actually equal to OB minus OA, which is square root of r square minus zeta square minus eta square, and on the right hand, so we have rearranged the term as shown in on the right hand side of equation number 26. Okay, let's read these statements. Parabolic approximations to the spherical caps require: number 1, we consider small regions on the zeta eta plane and on the xy plane about the z axis, and number 2, assume that the separation between the caps, which is capital R, so between the two caps, you know that between the two caps, left hand side cap and the right hand cap, assume that the separation between the caps, which is capital R, is large compared to the size of these small regions. So these approximation lead to that we can expand this the square root of this quantity in equation number 6 can be expanded as so 1 minus zeta square plus eta square over r square. The square root of this quantity can be expanded binomially, which is equal to 1 minus half. Within the parenthesis we have zeta square plus eta square over r square. So we have kept only the first two terms because r is so large that we need to keep only the second term and the third term in which r to the power 4 will be involved. We are not taking into account those terms. So just the first two terms are enough for the purposes that we remain in the Fresnel region. So you know that in order to apply this condition, we are substituting equation number 27 in equation number 26. So some terms will be cancelled out, and the simplified result is that a general point D or P1 lying on the left spherical cap takes the following coordinate system. So the coordinate of a point P1 or the coordinate of a point D are zeta, eta, comma r by 2, and within the parenthesis we have zeta square plus eta square over r square. And you know that we can replace r by capital Z in order to write the expression in more general form on the right hand side in equation number 28. So similarly, on the similar basis, we can write down the coordinate system for the point P naught lying on the right side spherical cap. So similarly, the coordinates of a point P naught lying on the right spherical cap with respect to the origin, that is point P, are given by, so coordinates of a point P naught are x comma y comma capital Z minus r over 2, and within the parenthesis we have x square plus y square over r square. So you can derive this one similarly as we derived the equation number 28. And you know that replacing a capital R by capital Z, you can write down this expression as we have shown in 20 number 9. Z provide us a more meaningful, a more generalized expressions. Now we can find out the distance between the point P0 and P1. We have calculated the coordinates of a point P1 in equation number 28. We have calculated the coordinates of a point P0 in equation number 29. Now we can apply the distance formula between these two points to calculate R01. So R01 is given by, so you know that we have to calculate R01 in this special case, because that's why we could not apply equation number 9, equation number 11 or equation number 14 of the Fresnel diffraction formula, because R01 was not simple in that case. Now you see that we have found R01 in equation number 30, and we have x minus zeta whole square plus y minus zeta whole square plus the difference of these z coordinates and the square root of the whole. So you know that expanding these one and applying the approximations which are given below, we have written that R01 is approximately equal to capital Z, and within the parenthesis we have 1 minus x into zeta over z square minus y into eta over z square in equation number 30. So this is the value of R that we shall use in the exponent in the exponent where R01 would exist. We shall replace R01 in the exponent by the expression on the right hand side in equation number 32. So in writing equation number 32 to its last expression, that is this one, we have used the following conditions, that is zeta square plus eta square over r square is less than 1, and x square plus y square over r square is less than 1. So equation number 31 was used in equation 30 to obtain the final result shown in equation number 30. Now you know that we have computed all the value of R, so we need to put the value of R in the Fresnel diffraction formula of equation number 4, which is reproduced over here. So we have the Fresnel diffraction formula in equation number 25 or 20 or in number 25, or just simple in equation number 4. The formula is u of xy, that is the field at the point xy, which is the field at the second spherical cap, is equal to z over iota lambda surface integral over s1, and the input field is u of zeta eta multiplied by e to the power iota k r01 over r01 whole square, and the elements are d zeta d eta. So you see that here we are going to substitute the value of R01 over here, which we calculated in equation number 30, and now in the denominator we are just putting R01 by Z, because here we are not putting the full substitution, we are just replacing it by Z square. No approximation is being used in the value of Z, because the formula will become very ugly, and moreover this Z square just contributes the amplitude of the field. So this factor is not very much important that we precisely calculate this one. So you know that in the third step we have e to the power iota kz over iota lambda z, and the surface integral over s1, which is the clear aperture, and within that one we have the field which is u of zeta comma eta in multiplied by e to the power minus iota 2 pi over lambda z, and within the parenthesis we have x into zeta plus y into eta, and the integration is with respect to zeta and d zeta and d eta. So you know that consider the last step in equation number 32, which is very important, because we have written x over lambda z by fx, and we have replaced y over lambda z by fy. So fx and fy are the Fourier variables we have represented over equation in the last step. So you know that if you recall the last step, the integral is nothing but the Fourier transform of the quantity u of zeta and eta. So the integral provides you you the Fourier transform of the field at the input spherical cap. The Fourier transform of this quantity will give you will provide you the field at the right spherical cap. So the Fourier transform of the field at the input spherical cap, the Fourier transform of that quantity will give you the field at the right spherical cap. This is the Fresnel diffraction formula, which gives the field u of x comma y at a point xy on the second spherical cap due to the field u of zeta and eta at the first spherical cap separated by the distance capital Z. In the denominator, we have used r0 approximately equal to capital Z. The discussion has been covered after equation number 5. Commentary on the Fresnel diffraction formula of equation number 14. So equation 14 was derived when the input field was known on a planar surface and the output field was determined on another planar surface parallel to the first but z distance apart. So we have given the description that in equation number 14, when we calculate the Fresnel diffraction formula, the both planes, that is the input plane and the output plane, both planes were parallel to each other, separated by a capital distance z, and both planes were the planes that is the field were existing at planar surfaces. And you know that in the present case the field are existing on the spherical caps, that is on the left spherical cap. At any point the field is u of zeta and eta. And you know that we have written equation number 18 is reproduced over here, which is the extended formula or the expanded formula of the Fresnel diffraction formula. We have already discussed this one, and you know that here we have the Fourier transform. Recognize that this integral gives you the Fourier transform of the quantities within the curly bracket, which is the field at the input plane multiplied by the quadratic phase factor at the input plane, which is e to the power iota k over 2z, and within the parenthesis we have zeta square plus eta square. And note that there was another quadratic phase vector related with the coordinates of the output plane, which is e to the power iota k over 2z multiplied by x square plus y square. Comparison with the equation number 32, which is this equation you see. So comparison with the equation number 32 reveals that the two quadratic phase factors, one is e to the power iota k over 2z into x square plus y square, the other involves zeta square plus eta square, are eliminated when we transform the problem from planar geometry to the geometry of the confocal spherical caps. So this is a very beautification, that is these quadratic factors are eliminated when you go from planar geometry to the spherical confocal geometry. Okay, in the case of confocal spherical caps, the field at the output cap is the Fourier transform of the field at the input cap multiplied by constant time e to the power iota kz over iota lambda z. If the input field is on a spherical cap and the output field is to be determined on a point on a planar surface, here we are talking about the planar surface, then only the quadratic factor this will be eliminated. So if the cap is spherical, the corresponding quadratic phase factor will be eliminated. So if we are using the input field on a spherical cap and the output on a planar cap, then you know that in this formula, that is in formula number 14, the quadratic phase factor which is related to the input plane and which is in this case the spherical cap, this quadratic phase factor will be eliminated, but only the spherical cap at the output plane, which we are now considering as a plane in which we want to calculate the field, this quadratic phase factor will stay there. Now if the input field is known on a planar surface and the output field is to be determined on a point lying on a spherical cap, then the quadratic phase factor this will be eliminated. So if the input plane is a planar surface and the output plane is a spherical cap, then you know that this factor which is related to the output will be eliminated. Kirchhoff diffraction formula can act as the basis of the derivation of a Fresnel diffraction formula for confocal spherical caps, whereas the Rayleigh-Fresnel diffraction formula cannot stand as the basis. Why? This is what you can answer this question if you have really understood my all previous slides. If you can understand, you can write down the solution of this equation yourself. So actually this is the end of slide number 43 of 43.